In this video, we use the first and second derivative tests from calculus to test for local extrema of functions, and we also talk about inflection points. You can see in this first problem that there are 4 functions to consider. For each one of those following, find the critical points, inflection points, and test them for extreme values, local maxima and minima, and then graph the function as well. We'll try to get as far as we can with the graphs without technology, but we will need to use technology to help us refine our graphs. Part A. F of x is this cubic that you see here. Take its derivative, you'll get a quadratic. F prime of x will be 3x squared minus 18x plus 24. That is a quadratic. If I set that equal to 0 and solve for the critical points, I certainly could use the quadratic formula, but I don't need to here. I can factor out a 3 and get 3 times in parentheses x squared minus 6x plus 8 equaling 0. I can factor that further as 3 times x minus 2 times x minus 4. And so your critical points are going to be the values where the derivative is 0. Those will be 2 and 4. Critical points are x equals 2 and x equals 4. How do you classify them? You use either the first or second derivative test. The first derivative test is in general a bit more powerful in a way that I'll explain here in a little bit. But you also can check with the second derivative test. Mark off on a number line the values of the critical points, in this case x equals 2 and x equals 4, and then in the remaining intervals that you see here, test the sign of the first derivative. We're talking about the first derivative test here. For example, when x is less than 2, I can test the sign of f prime by plugging in 1. F prime is a nice continuous function here. If f prime of 1 is positive, which it is, then f prime of x will be positive for all x less than 2. Yes, when you plug in 1, either here or in general, the factored form is a little easier. You get a positive number. 1 minus 2 is negative 1. 1 minus 4 is negative 3. A negative times a negative is a positive. 3 is positive. This is definitely positive. That's all I need to know. F itself is therefore increasing when x is less than 2. What about when x is between 2 and 4, like 3? In the factored form, I'll get a positive times a negative, right? 3 minus 2 is positive 1. 3 minus 4 is negative 1. That gives me a negative. That means f itself is a decreasing function over this entire interval. Testing the sign of the derivative at one point is enough to say f prime of x is negative over this entire interval. And then when x is bigger than 4, like 5, f prime is positive times positive times positive. That ends up being positive. So f itself is increasing. And what the first derivative test tells you now is that because f prime changes sign from positive to negative as you pass through 2, there's got to be a local maximum point at 2. There's got to be like the top of a little hill in the graph. That's going to be the shape of the graph there. And f prime changes sign from negative to positive as you pass through the critical point at 4. That means the graph goes down, then up. It's got to be a local minimum at 4. There's no global max or min here over the entire real number line, only local extreme points. What does the second derivative test tell you? If we find the second derivative, take the derivative of this, you get 6x minus 18, which is the same as 6 times in parentheses x minus 3. Well, first of all, there's something called an inflection point. If I set this equal to 0 and solve for x, I get a possible inflection point. And in fact, because the second derivative changes sign at 3 here, from, well, when x is less than 3, you get a negative second derivative, and when x is bigger than 3, you get a positive second derivative. The graph is changing from concave down to concave up. When it changes concavity, either from concave down to concave up or vice versa, that's called an inflection point. This is going to be an inflection point of the original function because the second derivative changes sign. That's not the same as the second derivative test, though, for extreme points. For the second derivative test, I plug in the critical points, 2 and 4, into the second derivative and see if I get a negative or a positive number. When you plug in 2, you get a negative, confirming the graph is concave down near 2, and it's a local maximum. And when you plug in 4, you get a positive quantity, confirming the graph of f is concave up near 4, and that's why it's a local minimum. Putting all these things together, along with the fact that, for example, f of 0 is negative 5, gives you a rough sketch of the graph of f. It's also a cubic, so the end behavior is going to minus infinity over here and plus infinity over here. It's got a slope of 24 at x equals 0. F prime of 0 is 24. And so it's got to go up pretty rapidly, have some x-intercept that I'm not going to find at a slightly positive value of x, reach a maximum at 2, a minimum at 4. Does it go back below the x-axis? That's hard to say here without technology. I used the technology ahead of time and saw that it did not go back below the x-axis. And so the graph looks about like this. I'm not putting a scale on the y-axis other than to say this is -5 here. This is a very rough graph, but let's confirm it with technology here. There I have the function plugged in. I picked this for the window. Let's see what we see. Actually, I'm going to make the window go a little different. Let's go -2 to 8 here, say. Let's see, that doesn't look right. Do I have the right function plugged in? Let me go back to my y equals screen. X cubed minus 9. Oh, that's supposed to be an x to the second power there, and that's why it looks wrong. Okay, now that should be fixed, and here's what the graph looks like. Yes, just like what I drew it there. Pretty good, okay. Maximum, local maximum at 2, local minimum at 4, inflection point at 3. The graph changes from concave down to concave up as you pass through 3. Part B. Now we have a 5th degree polynomial. Don't panic. It's doable. F prime of x is going to be 5x to the 4th minus 30x squared. I want to set this equal to 0 to solve for critical points. Factor as much as possible. A 5 and an x squared can be factored out to leave you with x squared minus 6 inside the parentheses. And that's going to have values, solutions at x equals 0. And if you think about it carefully, x is plus or minus square root of 6. And in fact, you can even factor it further as long as you don't mind using square roots in your factoring, like this. And that'll help you think about where the signs of this changes from positive to negative or vice versa. So the critical points are x equals 0 and plus or minus root 6. Let's draw our number line. Let's see, I'll put it over here this time. Negative square root of 6, 0, and positive square root of 6. And in this example, something a little different, and you might say not so typical, happens compared to the first example. What typically happens is that the derivative does truly change sign as you pass through critical points, typically. But that's not going to happen with every one of these critical points here. If you plug in a number less than negative root 6, which is between -3 and -2, like -3, for example, f prime of -3 here, leave a little space there, think about the sign here. You'll get a positive times, what will that be? That'll be negative. And this will be negative as well because, again, root 6 is between 2 and 3. -3 plus root 6 will be negative. Positive times negative is positive. This is positive here, so f itself is increasing. Plug in a number in here like, -1. You get a positive times a negative times a positive. This is negative, so f is decreasing. Plug in a number like +1. You get a positive times a negative times a positive. It's still negative. F is still decreasing. The first derivative test doesn't tell you anything about if it's low, local max, or min. In fact, the fact that the derivative is negative on both sides tells you it's neither. Somehow it's neither. And plug in a number bigger than 6, like 3, into the derivative. You get a positive times a positive times a positive. That's positive, so f changes to increasing. So the first derivative test is going to tell you you have a local maximum at negative root 6, a local minimum at positive root 6, and neither somehow at 0, even though 0 is somehow a critical point. What's going on there? Before we graph it, let's think about the second derivative and inflection points and the second derivative test. Take the derivative of this, you'll get 20x cubed minus 60x. Set that equal to 0 to solve for possible inflection points. Factor as much as possible. The second derivative equals 0 at 0 and plus or minus root 3. Root 3 is between 1 and 2. And in fact, if you draw another number line, you can see that the second derivative actually does change sign at each of these 3 points. These are going to be the inflection points. The second derivative changes sign, so the graph of the original function is going to change concavity. And I haven't used the second derivative test. How would I use it? I'd plug in these numbers into the second derivative. I will let you do that on your own. What you will get if you plug this number into the second derivative is a negative value, so the graph is concave of f is concave down. If you plug in this one, you'll get a positive value, so the graph is concave up, confirming a local max at the top of a hill at negative root 6 and a local min, the bottom of a valley, at positive root 6. When you plug in 0, you're going to get 0. 0 is not only a critical point, it's also an inflection point. That's hinting at what's going on here. If you graph this, and also note that f of 0 is negative 8, for example, negative 8, and that is a point on the graph, and that is not only a critical point, but also an inflection point. And mark off negative root 6, local max, negative root 3, inflection point, and positive root 3 and positive root 6. And also think about end behavior. It's a fifth degree polynomial with a positive leading coefficient. And well, it's hard to say without technology if this goes above the axis or not. We will look at the technology and see that it does go above the x-axis here at this local maximum. Inflection point here turns out to be above the x-axis as well. The graph is changing concavity. It's a little hard to draw here. It's going from concave down to concave up as you pass through that point. This point, again, is a critical point and an inflection point. It's got to change from concave up to concave down as you pass through that point. And the fact that it's a critical point means the tangent line is horizontal there. The slope is 0. That's the strange thing that's going on there. Another inflection point here and a local minimum here. Something about like that is what the graph looks like. Let's do it now. X to the 5th minus 10x cubed minus 8. Window. Let's try negative 5 to 5 for the x direction. And let's try negative 50 to 50 and see what we see for the y direction. Not too bad of a window. If I go a little bit bigger in the y direction, you could probably argue that it's better. Not too bad a picture of what we got for this function, okay? So that's the graph for part B. Local max here, local min here, neither there. Inflection points here, here, and about here or so. All right, part C now. C and D go a little quicker. C, f of x is 4x minus 2 times natural log of x. 4x minus 2 times natural log of x, which, by the way, the domain of this would be positive values of x. X has to be positive to make this defined in the first place. Its derivative is going to be 4 minus 2 over x, right? The derivative of 4x is 4. The derivative of minus 2 natural log of x is minus 2 over x, which is the same as 4 minus 2 times x to the negative 1 power. I want to set this equal to 0 and solve for x to find critical points. Think about it this way. Add 2x to both sides. You'll get 4 equals 2 over x. Then divide both sides by 4 and multiply both sides by x. You get x is 2 over 4, which is 1/2. And that is your one critical point. Think about the first derivative test. Mark off the critical point, test the sign of the derivative. Now, the derivative is defined even for negative values of x, but the original function is only defined for positive values of x. So I only want to think about positive values of x that I plug in here, like 1/4, for example. For a 2 over 1/4 is 8. 4 minus 8 is negative 4. This is negative, so f itself is decreasing here. You plug in a number bigger than 1/2, like 1. 2 over 1 is 2. 4 minus 2 is 2, which is positive. F is increasing. So the graph of f decreases, then increases as you pass through the critical point. The first derivative test would tell you, since f prime is changing sign from negative to positive, that you have a local minimum at x equals 1/2. Local min at x equals 1/2. We could also try to confirm that with the second derivative test. F double prime of x, looking right here and taking the derivative of that, is positive 2x to the negative 2, which is the same as 2 over x squared, which is positive for all positive values of x. The graph of f is concave up for all positive values of x, the domain. That would be another reason, based on the second derivative test, that you have a local minimum at 1/2. If you plot this function on your calculator, I'm not going to bother doing so. What you're going to see is something about like this, with a local minimum at 1/2. It never goes negative in value. This function, if you plug in different values of x, is always positive. And again, a local minimum at 1/2. It does go off to infinity as x goes to infinity, because 4x grows faster than 2 ln of x. So that makes this graph reasonable. There is a vertical asymptote here, because as x goes to 0 from the right, ln of x goes to minus infinity, and subtracting something like that makes the whole thing go to plus infinity as x approaches 0 from the right. Any inflection points? No. The second derivative is never 0, so therefore it never also changes sign. And even if you were thinking about a function that was defined for x negative, this still would not change sign, because and even if it were 2 over x to an odd power, it still would not change sign in a sense, because the function would not be defined at the vertical asymptote at x equals 0. Yes, it would change sign from negative to positive, but that would not be something to focus on for an inflection point. So that's part C. Sorry if that was kind of confusing. Part D, f of x is x times e to the negative 2x. And we need the product rule and chain rule to differentiate this. F prime of x, the derivative of x is 1. 1 times the second function gives you 1 times e to the negative 2x, plus the first function x times the derivative of the second. The derivative of e to the negative 2x is e to the negative 2x times negative 2. Set that equal to 0, solve for x. You can factor it. You can factor out an e to the negative 2x and get this. E to the negative 2x is never 0, so the only way this is 0 is when 1 minus 2x is 0, so your one critical point is at x equals 1/2. However, unlike the previous part, part C, this is defined for all x, not just x positive. So if I want to think about the first derivative test and think about a number line, I could plug in negative values for x. And against the fact that the derivative is still a nice function that allows you to argue why you can just plug in individual numbers, like 0, for example, into f prime, and you'll get a positive first derivative, so f itself is increasing over here. Plug in a number like 1, for example, you'll get a negative first derivative, so f itself is decreasing. F prime changes sign from positive to negative as you pass through this critical point. F itself changes from increasing to decreasing. That's why you have a local maximum at 1/2. Local max at x equals 1/2. What about the second derivative test and finding inflection points? The second derivative, if I differentiate this thing, I'll get, again with the product rule, I'll get that term and also this term. I took the derivative, the first function, e to the negative 2x times the derivative of the second. 1 minus 2x has a negative 2 derivative, plus the second function, 1 minus 2x times the derivative of the first. There's the derivative of e to the negative 2x. You can factor out e to the negative 2x. What's left over is a minus 2 there, and I got to distribute the minus 2 through here. Negative 2 times 1 is minus 2, and negative 2 times negative 2x is positive 4x. Set this equal to 0 to find possible inflection points. We get this equals 0, and this can be factored as 4 times x minus 1. And yes, this will change sign where this is 0. There is a true inflection point at x equals 1 because the second derivative is changing sign. If I also want to use the second derivative test to confirm this is a maximum, you could plug 1/2 into the second derivative right here. you would see you get a negative quantity. The graph is concave down near 1/2. Putting this all together gives you a graph that looks about like this. F of 0, by the way, is 0. Plug in 0 here, you'll get 0. So the graph goes to the origin. Maximum at 1/2. There's 1/2 right there. Inflection point at 1, it's going to change concavity from concave down to concave up. And in fact, this function does have the x-axis as a horizontal asymptote as well. As x approaches plus infinity, you've got an exponential decay times a power function. The exponential decay wins out, making this go to 0, and never negative when x is positive. So it's got to go toward the x-axis. It is negative when x is negative. In fact, it goes to minus infinity as x goes to minus infinity, because this exponential will grow as x gets bigger negatively. In number 2, we only deal with one function, and we just find and classify critical points, but it's got infinitely many critical points. Sounds scary. It's not quite as scary as it sounds. F of x is sine of x plus cosine of x. All right, what is the derivative? The derivative, this is a linear combination, a sum of two functions, so the derivative of it will be the derivative of this plus the derivative of that. The derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. So there is the derivative. To find critical points, we set this equal to 0 and solve for x. How in the world can we do this? We can't factor the left side, can we? Not in any typical way that comes to mind, but you can add sine of x to both sides and then divide both sides by cosine of x and get 1 equals sine of x over cosine of x. We're looking for solutions of that, but sine divided by cosine is tangent. Okay, now the inverse tangent function or arctangent function will give us one answer. I could write inverse tangent of 1, or I could write arctangent of 1. Those are the same quantities. And assuming your calculator's in radian mode, you can double check. This gives you pi over 4. But that's just one critical point, not the infinitely many we are after. Okay? Pi over 4, when your calculator's in radian mode, is the right answer for x, and you always assume in calculus that you're in radian mode unless said otherwise. That is equivalent in degree measured to 45-degree angle. So what are the other critical points? One thing to think about is the fact that the tangent function, tangent of x, is periodic with period pi, not 2 pi. So it's going to be back to a value of 1 every pi units. Thinking about the unit circle, when the angle is 45 degrees, pi over 4, but also add pi to that in degrees, that would be adding 180 degrees to 225 degrees in the third quadrant. That's going to be another critical point. Then back to an angle up here, 360 plus 45 degrees, 405 degrees. In radians, that would be pi over 4 plus 2 pi. Then 3 pi, then 4 pi, then 5 pi, etc. Also negative multiples of pi. The critical points can be written as x equals pi over 4 plus integer multiples of pi, n times pi, where n can be 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. Those are the infinitely many critical points. When n is 1, it simplifies to 5 pi over 4. When n is 2, it simplifies to 9 pi over 4. You also could write this as getting a common denominator as pi plus 4n pi over 4, or if you prefer, 4n plus 1 times pi over 4 would be another way to write that, those critical points. How do you classify them then? You could think about the first derivative test. Let's think about the second derivative test. The second derivative of this is going to be negative sine x minus cosine of x. If you plug in pi over 4 or any other answer here where n is even, I'm going to write this a little differently. I'm going to write 2n pi, where n can be any integer, corresponds to these answers when n is even. But now in this expression, n is 0, plus or minus 1, plus or minus 2, etc. Again, for emphasis, corresponding to these answers when n is even. Plug those in, you're in the first quadrant. The sine and cosine are both positive. In fact, they're both square root of 2 over 2. Two negative signs makes this negative. So at these critical points, f is concave down, and they are local maxima. If you plug in, well, let's add n equals 1 to this. Pi over 4 plus pi is 5 pi over 4. Plug in 5 pi over 4 plus 2n pi. You're at the angle in the third quadrant where both sine and cosine are negative in value, and combining them in this way with minus signs gives you a positive answer. So that means f itself is concave up, and these points correspond to local minima. Local maxima at these points, local minima at these points. I have now classified them. These are local max, maxes, plural, and these are local mins. I did graph it on my calculator ahead of time. You can do so on your calculator. Make sure it's in radian mode. F of 0 is not 0, by the way. It's sine of 0 plus cosine of 0, which is 0 plus 1 is 1. The y-intercept is 1. There's a maximum point at pi over 4. Let's say that's about here. The graph does have to go up. It's not a local max at 1. It goes up and reaches a maximum at pi over 4. Goes down and reaches a minimum at 5 pi over 4. And repeats. It is a sinusoidal wave. Turns out, I'll let you see if you can figure out why, the amplitude of this wave turns out to be square root of 2. I'll let you see if you can figure out why. So it also goes down to negative square root of 2. And this is going to be at pi over 4 minus pi would be negative 3 pi over 4, which fits this case when n is negative 1, I believe. Yeah. Got a local min there. And it's periodic, goes on forever and ever. That's basically what the graph looks like. Amplitude of square root of 2, period of 2 pi. I'll let you see if you can confirm on your own that the amplitude is square root of 2. In problem number 3, we have a parameterized family of functions. F sub a of x, my book doesn't use the subscript, but I am, equals x cubed minus ax, where a is constant, though what's most interesting is thinking about this function and what happens to its graph as a changes. For any constant value of a, you can make the graph, but you could change a and make a different graph. How does that graph get affected by changes in a? Part A says find all the critical points of f sub a. Let's do that first. So we need to take the derivative. Treating a as a constant, I'm differentiating with respect to x, and I get 3x squared minus a. Set that equal to 0, and solve for a. You get 3x squared equals a. So x squared is a over 3. So x is plus or minus square root of a over 3, which is only going to be two distinct real numbers if a is positive. It'll be one number, 0, when a is 0, and will be imaginary critical points when a is negative, which for calculus class, you don't think about that, okay? If this was a complex analysis class, you could think about it. So this is two critical points when a is positive, if a is positive. One critical point if a equals 0, and no critical points, no real critical points, if a is negative. Okay? That's the best way to describe the answer. Part B, find the value of a so that fa has local extrema at plus or minus square root of 3. And in part C, we're going to find the inflection points. I will, it's not part of the directions, but I will graph f sub a for different values of a so we can see these properties. We want local extrema plus or minus 3 occurring at the critical points. They got to occur at the critical points. And by the way, the first derivative will change sign. If a is positive, it'll change sign at the critical points. If a is 0, it does not change sign at the critical point. Let's assume we're in the case where a is positive. Well, that'll have to be the case if we have local extrema at this. So they're going to occur at plus or minus square root of 3, so we need to set square root of a over 3 equal to 3. And then we could also, in doing so, say that minus square root of a over 3 equals minus 3. Solve for a, square both sides, multiply both sides by 3. Looks like a equals 27 is the answer. That's going to where you have extreme values at plus or minus 3. If you plug in a equals 27 in here to double check it, 27 over 3 is 9. Square root of 9 is 3. You get plus or minus 3. And yes, when a is positive, f prime will change sign at these critical points. And so you will have local extreme values at plus or minus 3 when a is 27. Part C, inflection points. What's the second derivative and does it change sign? F double prime of x. Take the derivative of this, you'll just get 6x. Set that equal to 0 to find possible inflection points. X equals 0 is the possible inflection point, and in fact it is an inflection point because the second derivative will change sign at x equals 0. This is an inflection point. No matter what a is. The inflection point is independent of a. The critical points are not independent of a. What's going on here? What does the graph look like? When a is negative, it's x cubed minus ax. It's like x cubed plus a positive constant times x when a is negative, because two negatives make a positive. Its value at 0 is 0, and it's always going to have a positive slope when a is negative. The derivative will always be positive when a is negative. The graph is going to look like this. It is a cubic as well. Going to look like that when a is negative. It is a cubic with a leading coefficient that is positive. When a is 0, then the function is just x cubed. Looks about like that. It's got a slope of 0 there at the origin. And when a is positive, it's going to be going up, then down, then back up again. Graph still goes to the origin. It's going to look something like this. It is going to be an odd function. It's going to have origin symmetry. The critical points are negative square root of a over 3 and positive square root of a over 3. You can see it's a local max at negative square root of a over 3 and a local min at positive square root of a over 3. Our last two problems are graphic rather than symbolic in nature. The graph that you see here is the derivative f prime of some function f. This is f prime of x. Part A says on the graph, mark the x values that are critical points of f, and also say which critical points does f itself have local maxima, minima, or neither. Okay, this is the graph of f prime, not the graph of f. I will try to sketch a possible graph of f, but not right away. The critical points of f are where f prime is 0. Here, here, and here. Those are the critical points of f of x. How do you classify them? Use the first derivative test. F prime, this is the graph of f prime, changes sign from positive to negative at this critical point. So f itself changes from increasing to decreasing. That point's got to be a local max of f of x. Here, f prime changes sign from negative to positive. So the graph of f changes from decreasing to increasing. It's got to be a local minimum. That's a local min of f of x. But at this critical point, f prime is not changing sign. It's positive on either side. F itself is increasing on either side of that critical point. It's got to look like this. This one is neither. Okay? I will try to sketch a possible graph of f, but again, not yet. Let's also mark the x values that are inflection points of f. Do that in black. Inflection points of f are where f's graph changes concavity. Concave down to concave up, or concave up to concave down. Either way. If you think about it carefully, it's a little tricky to think about. That's got to be where f prime has extreme values. Like if the graph of f looks like this, concave down, then concave up, the slope is decreasing then before increasing again. The graph of f prime is going down before going up again. You have a minimum. The extreme points of f prime correspond to inflection points of f. The extreme points of f prime are, well, here, 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 and here. Those values of x correspond to inflection points. These are inflection points, x coordinates of f. Right there, right there, right here, and right here. The x coordinates of inflection points of f are at those x values where f prime has a local maximum or local minimum. Doesn't mean those points are on the graph of f, okay? So let's draw a possible sketch of the graph of f itself. This is the graph of f prime. This is telling you about slopes of f. They're positive at first, and then negative, then positive, and they stay positive. Where is the y-intercept of f? That's the only thing that's completely unclear. And maybe I shouldn't have even drawn a y-axis in here, because I have to draw an x-axis. Okay, this is not necessarily the origin, you might say. The vertical position of the graph of f is not determined. In fact, if I draw a plausible graph of f of x, any vertical translation of it will also be a plausible graph of f of x. Those are called antiderivatives, and they all differ by a constant that is added. So they're vertical translations of each other. Anyway, coming here, thinking about these x values here, should move these on down here, for both the critical points and the inflection points. Just trying to do this very roughly. These correspond to inflection points of f, and the other ones correspond to critical points of f that are maximum there, minimum there, and neither here. So what does the graph of f look like? It's concave up until you reach this point where f prime has a maximum, and then it becomes concave down, has a local max at this critical point because f prime changes sign from positive to negative, then goes down. Does it cross the x-axis or not? That's hard to say. I guess I'm drawing it in such a way that it's going to. An inflection point there before a local min here, another inflection point here before a neither point, critical point that happens to also be an inflection point right there. That's an approximation to the graph of f of x. And again, any vertical translation of that would be another possible graph of f of x. Our last problem is graphical in nature, and it has two parts that are both similar. In these pictures, there are two problems. Show the graphs of three functions, f, f prime, and f double prime. In each case, identify which is which. Okay, this is a little tricky. You got to do some experimentation in your mind, some hypothesizing, you might say. And so what you could do is you could start with one of these graphs, like maybe I start with the C graph, this bell-shaped curve, and I could ask, what does its derivative look like? And is it either option A or option B? And if it is one of those, then you're lucky. That is going to be the derivative of C. C has a positive slope here, zero slope there, and negative slope here. So its derivative has to be positive in value, then 0 when x is 0, then negative. Looks like this graph, B, matches. It looks like B is the derivative of C. And in fact, even more subtly, the value of the derivative is approaching 0 as x goes to plus or minus infinity, just like the slope of the C graph is approaching 0. So it looks like B is C prime, using bad notation, you might say. What's the derivative of b? Is it a? The slope of b is positive here, just like the value of a is positive. It's 0 right there, just like the value of a is 0. This is looking good. And then it's negative, just like the value of a is negative. 0 here, just like the value of a is 0. And positive here, just like a is positive in output. So the derivative of b looks to be a. And that would be also the second derivative of c. So, again, using sloppy notation here, c equals f, b equals f prime, and a equals f double prime, okay? Using these letters a, b, and c, both for labels of the graphs and also for function names. All right, do something similar in this one. What graph should I start with? It's not clear. Maybe I start with a. Slope is negative, then is 0 right there, then becomes positive. 0 right there, then becomes negative again. Is there a function, either b or c, that is negative, then positive, then negative again, and is 0 in value right where a has a 0 slope? It looks like, yes, looks like c is a prime. The graph of c is negative here, then 0 right when a has 0 slope, then positive when a has positive slope, then 0 again right there where a has 0 slope, then negative in value where a has negative slope. C is a prime. What's the derivative of c? Is it b? Slope is negative here, then 0 right there, just like b is 0 right at the same point, it looks like. Well, actually not quite. Not quite the same point. And yeah, confirmation, the graph of c is negative in slope over here, but b is not negative in value. So b is not c prime. Is a possibly b prime? Is a the derivative of b? That's another possibility. The slope of b is positive here, just like the value of a is positive. Slope of b is 0 right there, just like the value of a is 0. This is looking good. Slope of b is negative in here slightly, just like the value of a is negative. Gets back to a positive slope here. Just like the value of graph a is positive here. 0 slope there, just like a is 0. It looks like a is the derivative of b. A equals b prime. So, and that's going to be the same as, let's see. Sorry. What else can we say? B, a little confusing here. So c is the derivative of a, and a is the derivative of b. So c is also b double prime. It looks like then that b is f, a is f prime, and c is f double prime. You could check concavity as well. Let's end the video by doing that. Does the values of c tell you about the concavity of b? B is concave up here. Excuse me, this is b. B is concave down here, just like the values of c are negative. B is concave up in here, just like the values of c are positive. And then b becomes concave down over here, just like the values of c are negative. Yeah, that's extra confirmation. Thanks for watching.